In this video, I'm going to be dealing with calculations in acid-base theory, and therefore we have the first problem as calculate the pH of 0.01 molar hydrochloric acid. But here I'm going to first start with explanation of the pH in this case, of which in full it is potens hydrogen. So let's start with familiar expressions. You find if you look at, let's start with the ionization of water. Water, as you know, that is a weak electrolyte, and therefore in liquid form this ionizes partially to form hydroxonium ions, which would be aqueous, plus OH hydroxide ions, which would be aqueous. So you find that by balancing this, I put here a 2, and therefore everything is just balanced. Now, having got that, you find that we, by mass law of action, find that the dissociation constant of water represented by Kw, and we take here the assumption that at 25 degrees Celsius, we find that Kw by mass law of action, dissociation constant of water, will be the molar concentration of the hydroxonium ions plus multiplied by, let's say, the molar concentration of hydroxide ions and divided by the molar concentration of water, of which this one is constant. So out of that, you find that here we take the molar concentration of water to have no effect, and therefore molar concentration of water is taken to be constant in this case, and therefore we are going to say that Kw would be equals to molar concentration of hydroxonium ions times the molar concentration of the hydroxide ions in this case. So, but we know that Kw at 25 degrees Celsius, that this would be equals to 1 times 10 to the power negative 14 moles squared per, let's say we have dm to the power 6, or you can say that this is equals to 1 times 10 to the power negative 14 moles squared per liter squared. So all these units can be used to represent this as, let's say, units. You can use either of the two, which one you feel like is mostly appropriate. And therefore, from the above expression, this is considered to be the ionic product. Ionic product of water. Yes. So you find that out of that to get the pH, but you find like make you more understand this. You find that the pH of water, yes, is inversely proportional to temperature, and therefore, let's say the pH of water at higher temperature, you find that the pH reduces, and therefore water becomes acidic at higher temperatures. And in this case, another fact is that when water is left standing in air, you find that water, the pH also decreases in such a way that if I'm having water itself, you find that in air we have what we call carbon dioxide, and therefore carbon dioxide combines with water, and therefore this one weakly forms, let's say, carbonic acid. So you find that out of that, this is an acid, and therefore the pH has to reduce. So after this reducing, therefore if you leave water standing in air, in air, you find that the pH has to reduce automatically because of this kind of reaction. So these are just facts about how the pH of water changes. And therefore, so initially our question was requiring that calculate the pH of 0.01 molar hydrochloric acid, of which in this case I call potential hydrogen. Out of that, let's look at the pH of water. So the pH of water, pH of water in this case would be given by negative logarithm of the molar concentration of hydroxonium ions. And therefore, if I'm having this, but I know that I can calculate for this, but I know that Kw, which would be equals to, I'm having something that I'm having hydroxonium ions plus, then I'm having OH ions in this case. And therefore, if I want to get the mole concentration of the hydroxonium ions, I'm going to come and say Kw divided by OH ions, and therefore would be equals to, I'm having the mole concentration of the hydroxonium ions, of which in this case this would be a plus. So if I'm having the negative logarithm of this, and therefore I come here and say that if this represents this, and therefore I is inserted back here, so that means that I'm going to have pH, which should be equals to negative log of, I'm having Kw divided by the molar concentration of hydroxide ions, close this. If pH in this case is equals to negative log of Kw divided by molar concentration of hydroxide ions, this was enclosed, and therefore let's try to expand this using math and log, and therefore this would be equals to, let's put negative outside and enclose this. This would be we're having log of Kw divided by OH ions, molar concentration in this case, enclose this, and then work out with this, and you're going to say that this is going to be equals to, you're going to have equals to negative into log of Kw minus log of molar concentration of hydroxide ions, close this, and therefore you're going to have something which is going to be, this is going to be negative log of Kw plus, this is going to be the log of molar concentration of hydroxide ions, and therefore we are going to have something that's going to be equals to, this is going to be negative log of Kw is, we are having 1 times 10 to the power negative 14, yes, plus log of OH, and therefore this would be equals to, I'm going to have, this is going to be 14, yes, this is going to be 14 plus log of or concentration of hydroxide ions, and therefore this would give me the pH. We're going to say that pH would be equals to 14 plus log of OH ions. But you find that if I say pH minus log of the hydroxide ions would be equals to 14, and therefore this would be pH plus pOH, this is OH, would be equals to 14. So you find that this is another important expression that you should be quoting. This expression is very useful. Sometimes when you have pH, you have pOH, you can determine the other, or maybe one of them is lacking. So you find that you can easily determine the other. Now, let's work out this problem. We have calculate the pH of 0.01 molar hydrochloric acid. So you find that out of that, there are kind of acid you're dealing with. But HCl is strong acid, and therefore, if I'm to ionize it, you find that I'm going to come here and say hydrochloric acid, HCl. This one is, let's say, strong acid. That's what I can say, strong acid. And therefore, ionization is defined as the interaction of a covalent molecule with water. And therefore, if I have here, this would be, I'm going to say, hydrochloric acid plus water. That this kind of, the ionization that will take place here is a complete one, and therefore I'll have only one direction arrow, and therefore I'm going to have hydroxonium ions plus I'm going to have the chloride ions, be aqueous, and this would be aqueous. So out of that, if I'm calculating for the pH in this case, I'm going to say that pH, but look at this. Now, to determine the mole concentration of this, I'm going to say that if 0.01, the initial, let's say the molar concentration of hydrochloric acid, find that is 0.01 molar, and therefore, if 1 mole of HCl produces 1 mole of hydroxonium ions, that means that the molar concentration of HCl is the same as the molar concentration of hydroxonium ions, and therefore also the molar concentration of this is the same as this. So out of that, pH would be equals to the negative log of hydroxonium ions, and therefore I'm going to have H3O plus, and therefore I'm going to say that the pH equaling to negative log of 0.01, of which, now this kinds of, let's say this curve bracket is different from this one, simply because this one is just to represent the mole concentration of a certain ion that's present, and therefore in this case here now we're doing math, and therefore pH would be equals to negative log of 1 times 10 to the power negative 2. Yes, and therefore if we are at least like to work out this, this would be, if we look at this, and therefore I'll have, if I put this into my calculator, and therefore this pH would be 2, of which the pH, this is a strong acid, and therefore I expect the pH to be lower. Now let's consider this problem. Found that calculate the pH of 0.02 molar sulfuric acid. You found that if we look at sulfuric acid, that sulfuric acid ionizes to, we have sulfate, should be aqueous. When it interacts with water, which would be a liquid, and this would ionize completely to form 2 moles of hydroxonium ions, which would be aqueous, plus the sulfate ions, of which I'm going to have and 2 minus. This should be aqueous. Having known so, and therefore I come here and say that let's first balance this. You find that yes, everything, and I'm having a 2 here, 2 moles of water. So out of that, I'm having everything's just balanced. 2, 4, this is 6, and here I'm having 6, this is 4, this is 6, and this I'm having 6. So automatically balance. And therefore, if we have to calculate pH of this, but 1 mole of sulfuric acid produces 2 moles of hydroxonium ions. So we find out of that, that means that if 1 mole produces that, then number of moles of hydroxonium ions would equate to, I would have 2 times 0.02, and this would be molar. And therefore I'll come here and say that this is 0.04 molar of the hydroxonium ions in this case. And therefore, if I'm calculating for the pH, I'm going to say pH would be equals to negative logarithm of mole concentration of hydroxonium ions in this case. Now, having got that, then this would be negative log of 0.04 and close this. Having got that, this would be equals to, I'll have negative log of 4 times 10 to the power negative 2, which my answer in this case, this would be 1.3979, and then this would be the pH. So if I this is the pH, so if out of that, having obtained this, I can observe that the pH is very low. The pH is very low. It's like it is down actually. That means that because this acid ionizes completely, and therefore we expect the pH to be actually very low. Let's calculate the molarity of sulfuric acid. We are calculating the molarity of sulfuric acid whose pH has been given. So in this case, we know that when sulfuric acid interacts with water, we know that sulfuric acid, we are having here a form aqueous plus water, and this would be 2 liquid. We find that I'm going to have hydroxonium ions, which would be plus aqueous, and this I'm having 2 plus sulfate ions, which would be 4 here, 2 minus. So having known that, and this I'm having aqueous, and this is also aqueous, and every state is given. So we know that if the pH is given, we have the pH of which here we are seeing that 1 mole is producing 2 moles of hydroxonium ions, and therefore we know that negative log of mole concentration of hydroxonium ions, would give us this like the pH. And therefore, if I can get the mole concentration of the hydroxonium ions and compare to this molecular equation, I'm going to come here and say that this is going to be, if negative log of mole concentration of hydroxonium ions, which is a plus, would be equals to, I'm going to have 4.35. Now, having got that, I'm going to come here and say that that means that if I get the antilog of this, that means that I'm going to come here and say that if I'm having negative log, yes, base 10, we're working out of base 10, that's like of hydroxonium ions would be equals to 4.35. And therefore, I'm going to come here, this like, I'm going to take this negative here, this negative on the other side, and therefore I'm going to say that I'm going to have, in this case, if I'm having log of 10 molar concentration of hydroxonium ions is equals to negative 4.35, and therefore this is going to be the same as someone having, it's going to be like I'm having 10 to power negative 4.35 equaling to molar concentration of hydroxonium ions in this case. And therefore, if you work out this, you find that you're going to get something of this kind. 4.4668 times 10 to power negative 5 moles per liter. And therefore, this would be equal to the molar concentration of hydroxonium ions. Now, having got this, but we know that if the molar concentration of hydroxonium ions is this, but 1 mole of sulfuric acid produces 2 moles of HC of 1 mole of this produces 2 moles of hydroxonium ions. Therefore, that means that the number of moles of sulfuric acid in this case would be equals to, I'll have something that would be 1 out of 2 times, I'm going to have, this is going to be 4.4668 times 10 to the power negative 5. And therefore, I'm going to have something which is going to be 2.2334 times 10 to the power negative 5 mole per liter. And therefore, this would be the molarity of the sulfuric acid of pH. Now, with the strong bases and calculate for their pH, you find that here we're going to mostly deal with dissociation in this case. Now, for example, if I have sodium hydroxide, which is a strong, let's say strong salt, of which I'm going to have sodium hydroxide, which would be an aqueous, you find that it dissociates to form both negative and positive ions, of which I'm going to have sodium plus, which would be an aqueous, plus OH, which would be minus. And therefore, having got this, you find that I have seen this. After seeing this, I remember an expression of dissociation constant of water, of which we stated that Kw would be equals to, we are going to have the molar concentration of hydroxonium ions times the molar concentration of OH ions in this case. And therefore, you find that out of that, having got this, because I have this, that means that I can get the pH of this base, of which in this case we're having sodium hydroxide. And therefore, if the pH is equals to negative logarithm of the molar concentration of hydroxonium ions, That means that I have to make let's say hydroxonium ions the subject, because I know that Kw would be equals to 1 times 10 to power negative 14, of which this would be moles squared per liter squared. So I'm going to come here and say that Kw all over, let's say I have mole concentration of OH would be equals to the mole concentration of hydroxonium ions in this case. And therefore, I'm going to say that to get the pH of this, I'm going to say that pH would be equals to negative log of, I'm having here, this is Kw all over the mole concentration of OH ions in this case. And therefore, I'm going to get something that would be equals to, I'm going to have a negative outside log of Kw, yes, minus the log of OH ions in this case, of which I'm going to come here and say that this is negative into log of Kw. Inside I'm going to have, this is going to be plus pOH in this case, and if I open the bracket, this would be equals to, I'm going to have the same as having something which is going to be negative log of Kw plus, which is going to be a minus in this case, it is going to be pOH ions. So that means that pH is equals to, which is going to be, this is pKw minus pOH, and therefore I'm going to say that this is pH plus pOH equals to pKw, of which I can say pH plus pOH equals to 14, and this expression we previously obtained it. But since we are interested in the pH, and therefore I would prefer you leave it in this format, that pH is equals to pKw minus pOH, and in this case this would be equals to 14 minus pOH, and therefore this is how you would obtain the pH of a strong base, and therefore this is how you would undergo the calculation. Now let's consider calculating the pH of sodium hydroxide of 0.02 molar. So if we look at the dissociation of this sodium hydroxide, we find that sodium hydroxide, we have sodium hydroxide in aqueous state, that this would dissociate completely because it is a strong salt, and therefore we would have sodium hydroxide plus OH ions, hydroxide ions. And therefore we know that the dissociation constant of water is given by, we are having, or I'm going to first use the first method. So dissociation constant is given by, we are going to have, we have hydroxonium ions multiplied by, let's say, the hydroxide ions, and therefore I can say that from here, let me get the mole concentration of hydroxonium ions, and in this case I know that since sodium hydroxide ionizes completely, I know that the mole concentration of sodium hydroxide is taken to be equals to the mole concentration of hydroxide ions. And therefore, I can come here and say that I can calculate my pH very well. And therefore, I say that I'm going to have my pH, no, my pOH. And therefore, I say that this would be equals to 0.02 molar. And negative log of OH ions, I can get this would be equals to, yes, have this like pOH, of which in this case I'm going to be getting something that would be, in this case, this is going to be negative log of, I'm going to have something of this kind, 0.02, and it would be equals to pOH. So in this case, 1.69897, yes, that this would be equals to pOH. But I know that pOH plus pH equals to pKW, and therefore I'm going to have something. If I want pH, it equals to pKW minus this is going to be pOH, and in this case I'm going to have something that will be in this form, that I'm going to have pH equals to 14 minus 1.69897, of which my pH would be equals to, this would be 12.30103, and therefore this would be the pH at this case. So you find that out of this pH is higher because it's like this is a strong base, and therefore we expect the pH to be very, very high. So out of that, we're having 12.30103. Let's try using another method. And in this case, if I'm having that, of course, sodium, you had sodium hydroxide, which is aqueous, that dissociated to form sodium plus aqueous plus OH, which is also aqueous. So having known that this is like this, I come and say that, I know that KW would give me the mole concentration of hydroxonium ions, and then I'm having also mole concentration of, I'm having the OH ions, and I come here and say that KW divided by mole concentration of OH would be equals to the mole concentration of the hydroxonium ions in this case. And therefore, if I come here and say that this is, I'm going to have 1 times 10 to the power negative 14 divided by the mole concentration of hydroxide ions is the same as the mole concentration of the salt. The salt is soft, and therefore all over 0.02 be equals to the mole concentration of hydroxonium ions in this case. And therefore hydroxonium ions would be equals to, let's say hydroxonium ions would be equals to 5 times 10 to the power negative 13 moles per liter, and therefore the pH equals to negative log of 5 times 10 to the power negative 13, and then this would be equals to, 12.30103, of which is almost equivalent to this. So you find that whatever method you've used, you still approach the correct answer. So you just have to maintain the steps, and everything comes back to its initial position. If you look at this answer, it's the same as that answer. With all that said, thank you for watching, and see you next time.